Hello, everyone. Good morning. Good afternoon. Okay, so yeah, we missed one lecture from last Thursday, right? And I was trying to make some new slides into this current convolutional neural network lecture, and I found myself running out of time to make a video. So sorry about that, but I'm going to try my best to cover all the new content today. And this slide is not done yet, and it's not uploaded to the canvas yet. But I will do that later. So after the lecture. But the part before the object detection pages, before the object detection pages are the same as the old version of the slides, but I'm going to update that PDF file onto the Canvas system. Yeah. So, but as I said, I'm not done with the object detection parts yet. So we're gonna talk about the technique, talk about the first half of the technique of the object detection, which is about localizing the objects in an image first, just the first half, and then I'm gonna open the Jupyter Notebook and have some practical guides on using PyTorch to define ConvNet layers and to define polling layers, stuff, these basic skills of using PyTorch. Yeah. So as a warm up or as a practice for using Jupyter Notebook and PyTorch for implementing ConvNet models. Okay, so but first of all, we're gonna first cover what we haven't finished yet. So the slides, one slide ago, we have VGGNet, right? So it was first proposed in 2014, and it's a very typical deep convolutional neural network. And this VGG16 network was first proposed as a way to for large scale image recognition. And so the output layer here, if you notice, that's softmax 1000, which means it will output 1000 probabilities that tells which object that input image should belong to. Okay, so this is one of the very first early days application of convolutional neural network on image prediction on image classification tasks. But nowadays, I mean, 7 years later, the ConvNet is way more powerful than doing simple image classification tasks. Of course, image classification is still one of the most important or fundamental tasks yet, but I mean, ConvNet can be integrated into generative adversarial networks, GANs, in order to not just classify images, but also it learns to generate images that are realistic, that are basically very hard to distinguish from fake images. Okay, so we're gonna have a complete chapter for GANs, but it is after we have covered the generative have covered the ConvNets first. Okay, so VGG is the typical network, and it's basically the design idea is not that different from its predecessor, which is the AlexNet. Okay, it's just a polling layer following the conv layer, right? So what we're gonna first cover today is called Residual Network, or Resnet. And this network has made a significant breakthrough in making it easier to train very deep neural networks, okay, very deep convolutional neural networks. Okay, so because when we talk about deep neural network models, we have these vanishing and exploding gradients issue. Okay, the gradients and the activations in a network can easily explode because the network is too deep. Okay, and when we multiply all those parameters together from different layers together, then it's going to be very likely to explode or vanish. So Resnet provides a very good solution to this issue. It's called skip connection. Okay, and the basic idea is that it's feed the activation from one layer to directly to another layer. Okay, not just going through all the conv layers and the polling layers in the middle, but it provides a way to connect the earlier layers directly to much deeper layers. So the data that flow, the activations that flow within these layers can have an alternative way to bypass those conv layers and polling layers, to bypass those additional parameters. So you can choose a way with less parameters. Okay, so it makes the model much more robust against overfitting, and much more easier to tune, because the vanishing and exploding gradients issue is also kind of alleviated. Okay, so let's look at the building block of this so-called Resnet module. Okay, so here's a traditional way of a view of a traditional model. It's like the activation from layer L, right, feeds into the current layer L+1, and the L+1 feeds into the next layer. Okay, so in this each layer, so we're using regular neural network as a showcase here, but the same principle applies to convolutional neural network. We will first compute some linear readouts, which is the W times activation plus B, right? And then, for example, we use ReLU activation to compute the activation for this layer, which is AL+1, right? So that is a typical traditional network, right? And then the AL+1 is fed into the next layer, right? All right, so what we're gonna do here, right? If there's no Resnet connection, we will directly compute AL+1 using the linear readouts of ZL+2, right? That is a regular network. But in Resnet, what we will add to the network is that we let AL also directly connect to this addition step, which we call the skip connection, or it's a shortcut connection. Okay, so that means that part of AL, so AL not just goes through these networks in the middle, but also it has a shortcut to go through to directly enter the final computation for AL+1. Okay, so now AL+1 is the activation function applied to not just AL, not just to ZL+1, but also AL directly, right? So this AL is from these parts, from these shortcuts, while this ZL+2 is the previous, is the original one, original linear readouts, right? So we have the combination of both in the computation for AL+1, AL+2. Okay, so this is the so-called residual block. Okay, so with such a block, it actually allows for the training a model that is much deeper. Okay, so there are several types of shortcuts. So a directly copy of AL to from left to the right is called the identity. I think that is the most commonly used way. We just directly copy that value from the previous two layers before to the current layer. But when people first proposed this method, also there are some other ways, like we add some zero padding, and then we use a matrix multiplication to compute this. And turns out that this also works, but just for simplification, for simplified implementation, people will just directly use identity shortcut, which means we directly copy the activations. Okay, so that's a residual block. So using this block, we can connect all these blocks together, then we will have a complete so-called Resnet model. Okay, so we have these shortcuts like between two connections, between each of these two layers, right? And if we compare to a plain network, the additional part is the shortcuts connections. Okay, so it turns out that it has amazing effects in making sure that the model actually increases. Means the model has much better training effective against this so-called degradation effect. So the degradation problem is that the deeper model does not work better than shallow models. So the result, the figure here shows how the training error and the testing error decreases with the iteration number. So this is expected, right? But the counterintuitive part is that we have a deep model here that has 56 layers, which theoretically should work better than the shallower model that only has 20 layers, right? But the fact is disappointing. As you can see, the training error for this red curve is even higher than a shallower network, right? That is unwanted because we design a deeper model and we put in so much more parameters. We train it for much longer time, then it works even worse than the shallow model. Okay, so this degradation problem is one of the difficulties in actually tuning a deep model because of all kinds of issues, like overfitting could be one of the issue, but also the vanishing and decreasing gradients is also a significant issue. And this is a difficulty. And what Resnet can achieve is that the difference between actually the deeper model can actually works better than the plain model that doesn't have residual connections. So on the right, there are two plots, right? So if you look at these plots, it's using Resnet, and it's comparing a deep Resnet that has 34 layers with a shallower Resnet in this light green. So you can see the errors for this deep network is lower than the shallower network. So which means building a deep Resnet actually is worthwhile. It's worth trying because it has better performance. And in comparison, if it's just plain network that don't have the residual connections, then the degradation issue is still there. The network, the deeper network is worse than the shallower network. Okay, so this connection, this technique actually solves a big issue, solves a big problem when it first came out, and the people were very excited about this residual connection in technique. So as for the question of why residual network can achieve such a significant improvements in performance, we can have very intuitive explanations actually. So given a network, right, we have a deep network, and if we add some residual connections to it, then it actually means that we add some additional layers here, right? These two blocks are the additional layers when we compare to the upper one, to the previous one, right? So it means that we add these additional layers, and our initial goal is to increase the performance. But we are not sure about that. We don't know whether increasing 2 layers will actually increase the performance. Okay, so we have a risk. We are facing the risk that adding more layers can conversely decrease the performance of the model, right? So how do we? So we want to face this risk. So the way that we mediate this risk is that we add some shortcuts. Okay, so even if with the shortcuts, even if we have 2 additional layers, but we still keep the alternative, we still keep the other way, like we keep the option for the network to choose these shortcuts so that these additional layers are ignored or neglected. Okay, so it provides an alternative that we can still stick with the shallower structure, shallower architecture, rather than having to include these 2 additional layers. Okay, so this whole thing makes the deeper network much more secure, much more robust. So it provides a plan B, so that if the model finds that additional parameters, the additional layer doesn't increase the performance, then it can still choose to bypass those additional layers. Okay, so that is basically why the Resnet work in improving the deep model's performance. Yeah, and as a comparison, I think these figures are from the Resnet's papers, original papers. Okay, so you see the Resnet's, it uses more layers than the VGG19. Okay, so the VGG19 is a variant of the VGG16, and the only difference I would say from Resnet, so architecture-wise, the difference is that it has these additional connections. Okay, if we remove those connections, then the plain convnets, so the Resnet would be not that different from a plain convnet. Okay, and the results is also amazing to solve those degradation issue, and to make it much easier to tune a much deeper network. Okay, so that's for the Resnet. Okay, and what we're gonna cover next is the next another type of commonly used Resnet, commonly used convolutional network. No, it's called one-by-one convolution, or people would call it networks in networks. So this one-by-one convolution is a special type of convolutional layer. Okay, as the name indicates, it uses the filter not in size 2 by 2, 3 by 3, or larger, but it uses just the one-by-one filter. Okay, and this one-by-one convolutional filter is the building block of the next model that we'll cover, which is called Inception Network. Okay, and one advantage of this one-by-one convolution is that it saves significantly amount of computation needed for a convnet model. Okay. All right, so let's take a look of this one-by-one, the so-called one-by-one convolution. If like our input is 8 by 8 by 32, so let's review these numbers a little bit. So this 8 by 8 by 32, then of course, obviously it's not the original input. It's not an image, right? Because the image should have 1 or 3 channels, but it has 32 channels, which means this input is some intermediate input, some intermediate activations. It must be somewhere in the middle of a deep conv net. Okay, it's from the output from some previous activations, right? And the width and height is 8 by 8. Okay, so it has 8 pixels, and the depth is 32 channels. Okay, so that's volume inputs, right? So what we're gonna do is to apply one filter to that input. Okay, so the principle of the filter size still applies. It's a 1 by 1 filter, that's true, right? It's a little bit different from a 3 by 3, but that's okay. But we need to make sure that the size of this filter is 1 by 1 by 32, okay? Because the number of channels in the filter should match the number of channels in the input. So this principle doesn't change, okay? We need to make sure this principle holds. Otherwise, there's no way to conduct the convolution. Okay, so having this one filter applied to this 8 by 8 by 32, then our output would be like 8 by 8 by 1. Okay, so because this 1 by 1 filter doesn't shrink the size, so it's like if you have a, so if you only look at the one side of the input volume, right? So this is 8 by 8. We're just looking at the profile, okay? So if we look at the, if we apply a 1 by 1 filter, it should be just cover that small region, okay? And the dot product will be conducted to all the elements within this region. And in the case of this input, it will be a very long 1 by 1 by 32 long vector, which will be computed, which will be convoluted with this filter, right? And essentially it is just a summation of products, okay? So the 1 by 1 filter doesn't change the height and the width of the inputs, and the output is still 8 by 8 by 1, okay? And because the number of filters is 1, so the output has 1 channel. That is another matching relationship we need to keep an eye on, right? The outputs would have 1 channel if we only use 1 filter, okay? So another way, so if we use more filters, then the outputs will also change, right? So say in this step we applied 16 such 1 by 1 filters, then the output would be, of course, more channels, right? We would have 8 by 8 by 16 channels. Okay, so this essentially this 1 by 1 convolutional filter will preserve the dimensions of the inputs. Okay, it will not shrink or increase the size of input. So what's the point of this 1 by 1 filter? So actually it has a very broad of applications. So we're gonna first look at how this will help us save the amount of computation required in a convolutional layer. So you will see that it will reduce computation costs quite to a very large degree. Okay, so we have now the input in 8 by 8 by 64 channel. Okay, and we, as a comparison, we will apply 16 5 by 5 filters with same padding. So the same padding means that we will pad the inputs first, and then we apply this 5 by 5 filters so that the outputs is also 8 by 8. Okay, so the same padding depends on the filter size. And in this case, we will have the outputs 8 by 8 by 16 outputs, right? So now let's think about the detailed amounts of computation needed, okay? So the filter shape is 5 by 5 by 64, right? That is the size of one filter, okay? And the number of output elements is actually how much? It's actually 8 by 8 by 16, right? Because it is the size of this output volume, right? There's 8 by 8 by 16 elements in it. And for each element within this output volume, there is one time of convolutional computation needed, right? So the total computational cost measured by the number of multiplications, scalar multiplications needed, is the number of elements in the output volume, this quantity, times the size of the filter, right? So if we compute this equation, it would be 1.64 million numbers of multiplications. 1.64 times of scalar multiplication need to be conducted. Excuse me. So this is a very big amount of computation. Okay. So if you don't have this figured out, I hope you can go back to the slides for the convolutional filter. Okay, because the nature of the convolutional filter is that we apply this filter to each small region of the inputs, and what we're going to do is to compute the summation of products. Okay, and within that region there are that many numbers, right? 5 times 5 times 64, and for each number in it we will compute one product, right? So the total number of products needed would be these quantity times the left quantity times the right quantity. Okay, so it's a significant, it's a lot of number, a lot of computation needed. Okay, so actually we want to reduce the amount of time, and it turns out that if we reduce, if we apply the one-by-one convolution first, it will significantly save us amount of computation, right? We use the same input here, 8 by 8 by 64, and this time we will apply 8 one-by-one filters. Okay, and we don't need padding because one-by-one filters don't change the shape of don't change the width and height of the inputs, right? So the outputs would be 8 by 8 by 8, and this 8 is from the number of filters. We use 8 filters. Okay, so this intermediate volume is called a bottleneck. Okay, because it's thinner, and you will see that's why this is the case, why this is called a bottleneck. And then we will apply 16 filters, the same 16 5 by 5 filters that were used in the previous slide, okay, and with the same padding. And it will result in 8 by 8 by 16 outputs. So this is the output we want, right? In order to be compatible with the previous slide, we apply the same number of 5 by 5 filters. Okay, so let's decompose this new computation into 2 steps. Well, it's actually already 2 steps, right? We will first apply the one-by-one filter. So in this one-by-one filter step, convolutional step, the number of computation needed, we use the same principle. We use the number of elements in the output, which is 8 by 8 by 8, right? Elements, and each element we will use that amount of products to compute, right? It requires that amount of scalar multiplication to compute. So since the filter is 1 by 1 and the number of channels is 64, so it will be 1 by 1 by 64. So that will give us 32K times of multiplication. And then the second step, okay, so the filter is 5 by 5 by 8, that is the filter size. And the number of the elements in the outputs is 8 by 8 by 16. So the same, if we do this computation, it will be like 205K multiplications. If we add up together, that will give us almost 0.24 million times of multiplication needed. Okay, so what does this tell us? If we compare it with the previous slide, it actually saves the number of computation almost by 80%, right? So it's like 1.64 to 0.24. Okay. So it's a very significant amount of reduction of computation time, of computational cost, and the results outputs is the same dimension. Okay, it's the output here is 8 by 8 by 16, and if you look at the previous slide, it's also 8 by 8 by 16. Okay, so the difference is that we use some intermediate or bottleneck representation, bottleneck volume, okay, to reduce the necessary computation needed, because we use a 1 by 1 filter to first compress, like we have a very deep representation that has 64 channels. We compress that 64 channels to a thinner, to a much compact representation that has only 8 channels. Okay, so this compression, of course, it will inevitably lose some information, right? We have a very long vector that has 64 numbers, but now we use some filters, right, to like map this 64 vector to a 8 to a very short vector that has only 8 components. So so theoretically, this should cause some feature like reduce the performance a little bit, but it turns out that we can afford this. It's like even though the performance may be a little decreased, but since we saved so much running time, so much computational cost, the result turns out to be totally worthwhile. Okay, the trade-off is totally worthwhile. And I think in the paper that they call this 1 by 1 convolution a bottleneck network, because you see if we count the number of channels, we have 64 decreased to 8 and then increased to 16. So it's like there's a narrow place of the network that the representations becomes thinner. Okay, so that's the advantage of using 1 by 1 convolution here. And as I said, the 1 by 1 convolution filter is the building block for the Inception network. And in the Inception, the so-called Inception network is first proposed by Google. I forgot which year it is, and it was first called GoogleNet, and then there will be there are new versions coming out, like Inception v2 and v3. I think the most stable one is Inception v3. Okay, so what the Inception network try to solve is about the problem of how to choose the filter, different options for filter size. Like so far, we have gone through many networks that comes with different hyperparameters, like different types of filters are used. We have 1 by 1, 3 by 3, 5 by 5, different types of pooling, right? Different pooling with different filter size as well. So that is a lot of combinations. And how do we decide which one to use? So the idea of Inception Network is that why not we use all of them? Okay, so like we wrap them up and make them like parallel pipelines so that the data can flow into either into all the pipelines, all the parallel pipelines, and then we can wrap up all the outputs from each channel into some mixed representation. Okay, so in the example of the Inception network here, we use a 8 by 8 by 32 inputs. So the network's gonna like use these inputs and connect it to a 1 by 1 filter, and then it will result in this 8 by 8 by 64. Okay, outputs, like part of the outputs. Okay, so these outputs will be later concatenated with the other output from the in the other colors. Okay, so that is just one way to go. And the same inputs would also in parallel fed into this 3 by 3 filter. Okay, and of course, before this 3 by 3 filter, it will first enters another 1 by 1 filter, which I didn't plot here. Okay, because as the previous slide shown, if we directly apply a 3 by 3 filter, it's gonna be very computationally expensive, and then we can use the 1 by 1 filter to reduce that computational cost. So anyway, the second channel would result in an 8 by 8 by 128, for example. This brown or orangish intermediates representation. And the third way is a 5 by 5 filter, right, resulting in an 8 by 8 by 32. And the last way to go is simply a direct max pooling. Okay, so given these intermediate representations that are in the same shape, they are all in the same shape, are 8 by 8, right? But they are different number of channels. So we can simply concatenate them along this third dimension, which results in a much longer representation as a whole. Okay, so this representation is in 8 by 8 by 256 with all these different representations concatenated. Okay, and then this concatenated representation will be used as a representation will be used as the outputs for the next block of the network. Okay, so the advantage of such a combination of different flows, right, of different channels for the data to going through, it's kind of similar to the idea of Resnet, right? So the Resnet is like we have some deep layers here. If we have some representations from the previous layer, right, we can let the data to either choose to go through these deep these additional layers, or we can let it directly flow. And then we will concatenate these two, and we will have the activations for the current layer. That is Resnet, right? So actually the different flows here is kind of having the same purpose. It provides an alternative way for the previous activation to go through either one of these different flows, different channels, right? So we can have multiple ways to go through so that the model is more flexible. The model has more freedom in deciding which filters to use, which parameters to use. Okay. So this is the building block for the Inception network, and the Inception full model, Inception model is like we actually applied these. So this figure is from the original paper, and it's actually, if you turn it over, it's just like the way that I plotted in the previous slide. But as I said in the previous slide, I didn't show these one by one filters. Okay, so these one by one filters, for their purpose is to save the amount of computation time for these 3x3 and 5x5 filters applied directly. Okay. So yeah, and here is the V3 for the third version of the Inception network. Okay. So each block here, so you can think of this each block, they are just the visualization of the previous slide. Okay, the previous slide, it looks like this way. It's in a vertical direction, and if we place them horizontally, it will be like this. And the network is huge, and the interesting results, one interesting finding is that people find that we can either use the final output here. You see, there's a final output that starts with an average pooling and some dropouts, some fully connected layers, some softmax, and then use that representation to do image classification. So that is okay. That is one way, right? And the other way is that we can use the intermediate representations as well. Like, we don't need to wait until the last layer. We can just use the intermediate representations here to like compute, to directly apply to the can be directly used for the image classification tasks, which also turn out pretty good, having pretty good having pretty good performance. Okay, so that is for Inception network. So in the process of training, the model will trend towards the path that gives it most accuracy. So I don't think it will yeah, so yeah, I mean, you are correct. So during the training, the idea is that let the model to automatically adjust itself in choosing which way to go, in choosing which path to go through. Yeah, so it's because the gradient descent is to use the deviation between the prediction and the ground truth as a way to guide all the parameters to tune themselves, right? So in theory, the model should be able to adjust itself in choosing the best path to go through. All right. So at this point, we are almost done with the basics for ConvNets. Okay, I see another question. Will it adjust a mid-iteration or only on each new cycle? So theoretically, because we are training the model with mini batch, with data in mini batches, and in one iteration, we will feed into one mini batch, and we use that output to compute some loss, and the gradients will be computed and the parameters will be updated. So in theory, in each iteration, after in each iteration, the model will use the gradients to update itself. So theoretically, it has a chance to make adjustments for in each iteration. Okay. All right. So that's for the basics of the. We have covered the commonly used convnets so far. I'm not sure if I understand you, so could it adjust forward and backward then? So the adjustments of the weights actually occurs at the backward step. Okay, so in the forward step, the parameters are fixed. In the backward step, it will use the gradients computed to adjust all the parameters. Yeah. All right. So now let's look at a more theoretical question, like why does convolutional work? So first of all, the application that like the usage of very deep convnets on image classification task is amazing. It's like it saves a number of parameters, right? It saves computational resource, and it's achieved amazing performance in terms of accuracy. But people also explore why convnet works. Okay, so the one explanation is that actually the filters only is a small set of computation, right? The filter is a small set of filters. So we use the same filter to scan the different parts of the input image. So this mechanism is called parameter sharing. Okay, so it basically tells that a feature detector in one place is also probably useful in another place, right? Because we are using the same feature to scan the different places. And that also means the features that the parameters that we learn actually captures some universal patterns in the image, but not just to some specific patterns that are only exist in some particular regions, right? So that feature, the parameters capture the overall characteristics of the input image, right? And the second advantage of convolution is that is obvious. It's sparsity of connections. It's not like fully connected regular neural network. It doesn't have to doesn't need to compute all the one-to-one mapping parameters defined in the weight matrix, right? So altogether, we have fewer parameters. Okay, so that means the model would be more efficient in generates to learn some general knowledge about the general patterns in image, rather than to describe the idiosyncrasies in the data. Okay. So another term that people use to explain why conv network is called translational invariance. Okay, so it's also I think a kind of is in aligned with our common sense, like because when we see pictures of animals, for example, human mind has the capacity to generalize, right? After we have seen the picture of a cat, and we are able to recognize another picture of a cat that is just slightly different, right? So the convnets have such a architecture that is able to recognize different to recognize the same picture or the same objects after some slight changes to the pixels. Okay, so it has a very good performance in keeping the knowledge invariant, the knowledge learned invariance, even if there's some slight changes in the inputs. Okay, so that is basically how ConvNets, the superiority of ConvNets in image-related tasks can be explained. Okay, and a little bit technical details about backpropagation in the convolutional layers and the poly layers. Okay, so we don't need to like implement this nowadays because the backpropagation is handled by the machine learning frameworks automatically. But it's not that different from a regular network. We need to go in a backward style from the gradients of the Z of the current layer and then go back to the previous layer, right? And since now all the parameters exist in these filters, right? So what the activation, the gradients of the previous activations is basically the cumulative summation of the DZs times the W's, and the W is the filter here. And the DW also needs to use the A slice. So A slice is the elements within this cube defined by the region of the filter. Okay, and the DW, it's just the DZ itself. So these you see the equations here used is basically an analogy to the backpropagation equations used for a regular network. Okay, so essentially this is the same backprop algorithm that needs to be implemented. Okay, so ConvNets with PyTorch. I think I'm gonna skip this slide because it's too many lines of code, and actually in the assignments you will be asked to implement one of such a network. It's not necessarily as deep as AlexNets, but you will have some chance to practice how to make the different layers connect to each other with compatible numbers. All right. Okay, I see a question. ConvNets best build suited for image recognition. Yeah, ConvNets. I mean, the majority of the applications are about image and the video, about those data that are in volumes. Okay, so image is the most typical example. But ConvNets is also useful in textual data. I think you will be more familiar with it if after we talk about the recurrent neural network. So when text data is modeled, when language is modeled, the input at each time step, say a word, is modeled as a vector. A word is a vector, so this vector can be 300 dimensional or 100 dimensional, and those vectors, if a sentence has 5 words, then that will be a 5 by 100 matrix, right? So that 5 by 100 matrix, some models apply a convolutional network on top of these 5 by 100 vectors. And the convolutional network itself also achieves some satisfactory performance in predicting say the sentiments of this sentence, or to predict the semantic content of this sentence. Okay, so generally speaking, ConvNet is everywhere. It's not just to ConvNets. But nowadays, for language tasks, people find that other different types of models, like the most recent attention-based models is much more performance than ConvNet. Okay. So yeah, let's look at the next chapter. So we're gonna talk about the object detection task as an application using convolutional network. Okay, so it's an extension on top of this image classification task. You will see a lot of common places, and also you will see the differences. Okay, so I have to go a little bit earlier today, so I will spend the rest of the, I will spend 5 more minutes onto these slides, and I'll leave the class earlier around 5 o'clock. Yeah. So yeah, next, I think on this Thursday, we can also, we can finish the part for the object detection. And also I will go through the slides that I prepared, the Jupyter notebook that I prepared for convolutional operations. Okay. So object detection is a, I would say a pretty, it's a complex task. It's a complex task. Okay, so it's not just about to classify one image. Okay, it's about use a sliding window to go through an input image and tries to find the region that contains an object in it. Right. So the first step towards object detection is that we want to do more than image classification. We want to not just recognize the objects. We want to not just classify the image, but also provides a localization, provides a local, find the location of that recognized object. Say a classifier, if I have trained a classifier, then it is able to take this input image as inputs, right? And then it is able to tell, okay, this is a picture of a dog, right? But if a model, if I want to do localization at the same time, then the model should also output some like rectangles, right? A box that tells the dog is within this box. Here is the dog, right? Here's the location of the dog. I wish our model to do so, okay, in order to conduct effective object detection, okay? And also, beyond the localization, the next step is to detect multiple objects, right? If there's input, there are multiple similar objects, then I wish to output the locations in multiple boxes, okay? So that is basically how the model should be developed sequentially. We need to have something easier done, right? The classification needs to be done, and then the localization needs to be done, and then we need to detect the multiple local locations, right? So this, let's look at this classification with localization problem, okay? And as a comparison to the pure classification pipeline. So if it's just a pure classification, then given the image, like an image of a car, right? We can design some ConvNet, right? No matter architecture we want to use, it's a ConvNet-based model. Then the outputs would be a softmax layer, okay? A softmax layer provides a outputs a sequence of probabilities, okay? It tells the probability of this image is a car or a pedestrian or a motorcycle or it's just background, okay? So it should be able to generate such outputs, y hat, right? But for localization, we need to do more than that. So given the inputs and the model, we wish the model to output not just the classes, but it should be a combination of this, of this bounding box coordinates, okay? So this bounding box coordinates and the class labels, okay? So this BX, BY, BH, BW, and the class labels, these are what we need, okay? So as a comparison to this, this one needs to be output here, right? But in addition, we need to we need to output this left part as well. Okay, and this left part information contains the coordinate information for these boxes. Okay, so that is the basic difference between a pure classification pipeline and a classification with localization. So I think I'm gonna stop here, and I will upload the slides and the video to Canvas later. Okay. Yes. If you don't have questions, I'm gonna stop the recording now.